Evaporation or vaporization, two different words describing the same thing. It's a physical change, a change of state, going from a liquid state to a gas state. Not a chemical reaction, just a physical change. And we can look at how fast or how easily something evaporates or is vaporized. The rate of vaporization is going to increase if you increase the surface area of the liquid, if you increase the temperature of the liquid, or if you get a lesser or weaker strength of intermolecular forces. So if we think about this, think about, say, a towel, and you want to make it dry. What's a good way to get it to dry? Hang it on the line. When it's 105 outside, you hang it on the line. It's dry almost before you can get back into the house, right? Why does that make it dry faster? It's hot. Okay? The warm air gives more thermal energy to the particles of water that are making the towel wet and makes it easier for them to evaporate, to go into the gas state. Do you want to spread the towel out in the sun, or do you want to bunch it up in a lump? You want to spread it out. You want to give as much surface area as possible, because things can only evaporate from the surface. They can't evaporate from the middle. Think about this. Take a cup of water, take 2 cups of water, spill one on the floor, and leave one sitting on the counter. Which one's going to evaporate first? The one on the floor. Because it's spread out, it has a larger surface area. It'll evaporate faster. So, surface area, temperature. What about intermolecular forces? Well, alcohol has weaker forces of attraction between the molecules than water does. And I think we know from experience, if you've got alcohol on your skin, it evaporates very quickly, much more quickly than water does. And that's due to differences in the strengths of intermolecular forces. So if we have a liquid that evaporates easily, it's called a volatile liquid. Things that don't vaporize easily are called non-volatile. So when you're painting, one of the things that they list on the paint is VOC, volatile organic compounds. And so volatile means those are the ones that are going to evaporate into the air. That's what's going to make the smell, and you'll be breathing that in when you're painting. So let's think about the process of evaporation. So here I have a beaker full of little Mickey Mouse head water molecules. And they're just like, swimming around next to each other. They have kinetic energy. If you have one with high kinetic energy, it's going to be able to break free from the attractions of the nearby molecules and go into the gas state. Once it's in the gas state, it's just going to travel in a straight line until it bumps into something. If something's traveling down and hits the surface, then it's going to get trapped again. So my analogy for this is a game of Red Rover. You guys know what Red Rover is? Yeah. It's not really tag. They don't allow tag in school anymore either. They don't let you play Red Rover anymore because people can break their arms. But Red Rover is where you get 2 groups of kids on opposite sides of a field, and they hold hands. They make 2 lines. And the goal is to keep the other team from getting through your line. And so the leader on one team says, Red Rover, send Sally right over. And then Sally from the other side runs at your line, and you're holding hands, and you're trying to stop her. You can see how people could get hurt doing this. Try to stop her. Well, she's going to pick the weakest people to get through, right, if she's any good at this. And she's going to run fast, right? The faster you run, the more likely you are to break through. So there's a Red Rover line here. Its intermolecular forces are the people holding hands. And the thermal energy is how fast these other molecules are heading toward the surface. If they have enough speed, they're going to break through and they can evaporate. If you heat this up, you increase the amount of thermal energy everybody's moving faster, there are more that can move fast enough to break through the line. If the intermolecular forces are weaker, like in alcohol or gasoline, this is like playing Red Rover with kindergartners instead of playing with the, Fresno City College football team, right? You're going to have a lot harder time breaking through the football team's line than the kindergarten line. Why? Well, the strength of how they hold hands is different. The football players are stronger than kindergartners, right? So if we look at a particular temperature, the temperature is a measure of the average kinetic energy of the molecules. Well, you've got an average, you've got some that are high and some that are low, a bunch in the middle. And so this curve here represents the kinetic energy of the different molecules. So the fraction of molecules with this kinetic energy, kind of in the middle, is pretty high, and the fraction with very low kinetic energy is very small, but also at the high end, there's a few molecules that have much higher kinetic energy than others. You okay with that? So most of them are in the middle. And you think about people running or something, there's, kind of everybody's like in the middle, but some people are really fast and some people are really slow, right? So the really fast ones, even at a low temperature, have enough kinetic energy. This is the amount of kinetic energy needed to break through and evaporate. The minimum speed needed to break through that Red Rover line. So this area here under the blue curve is how many molecules can evaporate. If you increase the temperature, then you're moving this curve over, the average kinetic energy increases. It actually spreads out as well. You get more variation now. And you have more molecules that are able to escape. And so it will evaporate faster at a higher temperature. Does that make sense? When stuff is evaporating, it's the high energy molecules that are escaping. If the high energy molecules escape, what does that do to the average kinetic energy of what's left? It decreases it. As water evaporates, the high energy particles leave, taking their thermal energy with them, and the remaining water becomes slightly cooler. The opposite of evaporation is condensation, something going from a gas to a liquid. They're opposites. If we have evaporation and condensation happening at equal rates, we have what's called a dynamic equilibrium. And the number of gas particles above the liquid is going to remain constant. If you have gas molecules, you have a pressure from the gas. That's called the vapor pressure of the liquid. It's the partial pressure of that liquid in its gas state above the liquid. So let's look at a picture here. So here we have an Erlenmeyer flask with some water in it. And initially, there wasn't any water in the gas state. So there's water here, and it's going to evaporate. As it evaporates, and we've got a stopper in here so that it can't escape. As it evaporates, now we have water molecules in the gas state. These particles are going to exert a pressure, right? Because they're going to bounce against the walls. They're going to exert a pressure. Is it a big pressure? No, but it is a pressure. They're going to zing around here, bouncing off the walls, literally, until they happen to bounce and collide with the water, and then they're going to get stuck. That's condensation. So we have a rate of evaporation that depends on the surface area and the temperature. The rate of condensation depends on how many molecules are in the gas state. If you have more molecules in the gas state, then more of them are going to collide and get stuck. So initially you only have evaporation because there's nothing to condense. As you get more and more gas molecules, the rate of condensation increases. The rate of evaporation stays the same. Eventually, you'll get to this point where the rate of evaporation and the rate of the condensation are the same, and you've got the same number of gas molecules up there all the time. Are they the same gas molecules? No. They're constantly shifting and turning over. It's a little bit like an airport. Busy airport in the middle of the day. You've got planes coming in, bringing people into the airport. You have planes leaving, taking people away from the airport. Roughly, probably the same number of people in the airport at all times, but it's different people all the time. If the rate of incoming, let's say that this is the gas state is the airport. Okay, so initially the airport was empty. We've got people coming into the airport. Nobody can leave if there isn't anybody there, right? So once we get some people in the airport now, as the planes take off, people will leave. But people are still coming into the airport as well. So people coming in, people leaving. And if the rates of coming and going are the same, then the number of people here is constant. That's going to be a constant pressure, the partial pressure of water, called the vapor pressure of water. The rate of condensation is going to be affected by the surface area of the liquid. If you have a larger surface area, the rate of condensation will be greater, but also the rate of evaporation will be greater. The rate of condensation is not affected by temperature. The rate of evaporation is affected by temperature. So the vapor pressure of this gas is only affected by the temperature of the liquid. So in lab, we went to the CRC and we looked up the vapor pressure of water at the temperature that our experiment was at. Because the vapor pressure of water depends only on the temperature of the water. Any questions? So quiet. So vapor pressure increases with increasing temperature, decreasing strength of intermolecular forces. So if you have weak intermolecular forces, you're going to have a higher vapor pressure than if the substance has strong intermolecular forces.
Can you explain what the condensation was again?
Sure. Explain the condensation again. So condensation is once we have some gas molecules up here, they travel in straight lines. They go boing, 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 until they run into the liquid. They're going to get trapped. They're going to get stuck. So the rate of condensation is going to depend on how much surface area there is, because if there's a big surface area, that's a big target and more of them are going to hit it. But also you'll have greater evaporation. And so the surface area of the container does not have an effect on the vapor pressure. The temperature here doesn't affect the rate of condensation either, but it does affect the rate of evaporation. Higher temperature, higher evaporation rate, so you're going to have more particles here and a higher pressure. Was that good enough? The boiling point is the temperature at which the vapor pressure of a liquid equals the atmospheric pressure above it. Yes?
Real quick, wouldn't condensation be affected by surface area and temperature too, just like evaporation?
It's not really affected by temperature,
Okay, like just surface area?
just surface area. So when the vapor pressure has increased to a point where it's equal to the pressure above, then we start to get evaporation occurring within the body of the liquid. We see these bubbles form. The bubbles are the gas state of the water. And then because those are less dense, they will rise quickly to the surface, and those gas molecules will escape. So at the boiling point, we've got enough thermal energy that we're forming bubbles inside the liquid instead of just on the outside. When you get to that boiling point, and you try to heat it more and more and more because you want the temperature to be higher. You cannot increase the temperature above the boiling temperature of the liquid because you have all the higher energy molecules escaping and taking their energy. And as you put more energy into it, trying to increase the temperature, you're just going to cause it to boil faster. The temperature remains the same. This is something that's not intuitively obvious. So you can try this at home. Get a pan of water, stick it on the stove, put a thermometer in it, look at the temperature. When it first starts boiling, crank it up as hot as you can, look at the temperature. It's not going to change much. It's going to be 100 degrees Celsius at 1 atmosphere of pressure. The temperature will not go up until all the water has boiled away, until you just have gas. And then the pot gets really, really hot. It starts smoking and you have all kinds of trouble. This is what's called a heating curve. So it's a graph of the temperature here in degrees Celsius versus the amount of heat that is added. We don't really care what the unit is here, but we're adding heat. So if we take water at 20 degrees Celsius and we add heat to it, makes sense that the water's going to heat up. It's going to get warmer, right? So we add more heat, the water gets warmer and warmer and warmer and warmer. And as that happens, the vapor pressure of the water goes up until it gets to 1 atmosphere. At 100 degrees Celsius, the vapor pressure of water is 1 atmosphere, and it begins to boil. Once it starts boiling, the temperature is going to remain constant, as all of this heat that's added just goes into more rapid boiling. Once all of these gas molecules have broken loose from each other and we just have steam, then if you keep adding heat, the steam temperature will increase. Any questions? So evaporation is an endothermic process, and this one makes sense. Think about, well, how would you melt an ice cube? I'm sorry, not melt an ice cube, that's something else. How do you get a liquid to evaporate faster? Well, you heat it up, right? That's why we put a towel out in the sun or stick it in the dryer and turn on the dryer. Because you heat it up, you put energy into it to get it to go into the gas state. Endothermic. The system is absorbing heat because it needs energy to break those particles away from each other. Our body takes advantage of this through sweating. The reason we go outside on a day like today and you get all sweaty, because your body's like, hey, I'm too warm, I need to cool off. And if I coat the skin with water, the water evaporates and it takes energy away and it cools the skin. If you get a breeze, that's going to help because it'll take those molecules away faster. If you have high humidity, that's going to slow down the rate of evaporation. Humidity is the amount of water in the air in the gas state. So the more humid the air is, the slower the evaporation of your sweat will be. And I can tell you from growing up in the Midwest, where we have days, like the day my husband and I got married, it was 95 degrees and 95% humidity. I mean, the air was almost dripping. And you can sweat, and you will sweat, but it doesn't do any good because there's nowhere for that sweat to go. You just are wet and miserable. So yes, it's hot here, but it is a dry heat, and that does make a difference. Does it make it pleasant? No, but it's better than wet heat. Condensation is the opposite of evaporation. If evaporation is endothermic, condensation must be exothermic. This does not necessarily make sense. When something condenses, though, a gas condenses, when steam condenses, it releases energy. Steam will cause a very nasty burn because as the steam condenses onto your skin that's cooler than it is, it releases a tremendous amount of heat, causing a burn. This exothermic nature of condensation is also the reason that overnight temperatures do not get as low when the humidity is higher. So we've been through a period recently where it was really hot during the day, and then it maybe only got down to 70 at night, right? It's just like you go outside and you're expecting it to be refreshing, and it's like, ugh. It's just icky out there, right? And it feels humid. It feels moist. The air is damp. That humidity in the air doesn't allow the temperature to get as low, because as that humidity condenses on things, it releases energy and keeps the temperature up. Of course, we can quantify this. How much heat does it require to vaporize something? Well, we call that the heat of vaporization. It's given the symbol delta H, VAP, for vaporization. Amount of heat needed to vaporize 1 mole of liquid. So if you're vaporizing water at the normal boiling point, it's going to require 40.7 kilojoules for every mole of water that goes from the liquid to the gas state. So that's what's happening as you put heat into the boiling water. We're using that energy to convert from a liquid to a gas, and that's where the heat is going. It's not going into raising the temperature. Delta H here is positive because this is an endothermic process. Energy goes in. It's positive. Just like when money goes into your account, the bank shows it as positive on the statement. The same amount of heat is involved when you have a mole of gas condensing. So you heat you vaporize 1 mole of water, it takes 40.7 kilojoules. If you condense 1 mole of steam, it's going to release 40.7 kilojoules. Energy is conserved. You cannot create energy or destroy energy by evaporating and condensing water. It'd be kind of cool if you could, but we can't. What goes in comes out later. Here, delta H is negative because condensation is an exothermic process, and so this is the amount of heat that is released. Okay? So we can use the heat of vaporization to calculate how much energy would be needed to vaporize a certain amount of liquid. It's a convenient conversion factor between moles of liquid and amount of heat. So here's a table from your textbook giving a couple of different liquids, their normal boiling points, the heat of vaporization at that normal boiling point, and also the heat of vaporization at room temperature. So you'll see that these heats of vaporization at room temperature are slightly different, slightly higher than what you have at the boiling point. You do not need to memorize these numbers. Those would be given to you in a problem on a test. So let's see how to do that. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. And they tell us the heat of vaporization is 40.7 kilojoules per mole. So what do we have? We have 2.58 kilograms of water, and we have 40.7 kilojoules per mole. And we're trying to find kilojoules. Calculate the heat in kilojoules. So this is where we need to end up, and one of these is going to be our starting point. We can approach this using dimensional analysis, not really even getting what the numbers mean or anything. You can just look at the units and figure it out. So we look at these, this is just a single unit, this is something per kilojoules per mole. So this is most likely what we're going to start with, and this is going to be a conversion factor. So we're going to start with kilograms, and we need to get from kilograms to kilojoules. Well, this relates kilojoules to moles. So mole is going to be the step right before kilojoules. So moles. So we're bringing it in here a little bit, getting closer. How do we get from kilograms to moles? We need grams in between, don't we? We can convert kilograms of water to grams of water, and then we should be really good at converting grams to moles by now, just using the molar mass. So write the path out, and then just follow the steps of dimensional analysis. So we've got 2.58 kilograms of water, and we're going to convert that to grams of water, and then to moles of water, and then to kilojoules. So we put the previous unit in the denominator. We want kilograms down here so they cancel out. We want grams down here, and we want moles down there. Well, kilojoules per mole, that's this guy right here. 40.7 kilojoules for every mole. 40.7 kilojoules per 1 mole. Grams to kilograms, we should have a good handle on that by now. Kilo means 10 to the 3. So I've got the prefix kilo on the bottom. I'm going to write what it means on the other side. 10 to the 3. So 1 times 10 to the 3rd grams is the same as 1 kilogram. And then in here, grams to moles, we need the molar mass of water. So if you calculate that, you'll find that it's 18.016. So we take 2.58 times 10 to the 3rd divided by 18.016 times 40.7 equals 5828.48. There's more digits. How many significant figures should my answer have? 3. So the 5, the 8, and the 2. So this is the 3rd sig fig. The units here are kilojoules. I look at the next digit. That's my decider. This is 8. That tells me I need to change the 2 into a 3. So I'm going to keep the 5 and the 8. I'm going to change the 2 to a 3. This decider is to the left of the decimal point. So anything between this last digit that I'm keeping and the decimal point, I have to replace any of those digits with 0. So this would be 5830 kilojoules. The answer is not 583 because it's 5,000. Okay? You can also put it in scientific notation, and that's better. So it's that many kilojoules. Any questions? Yes?
Will this be a common pathway for heat of vaporization?
Well, sometimes it's kilograms. It could be milligrams. They might just give you moles. So there's all these different variations. But this is a fairly common path. You know. There are so many different kinds of problems that you can run into that I can't specifically teach you each type of problem. We need this overall approach. When we learn the approach called dimensional analysis, then we can apply it and figure all of these different situations out. This one's a little more challenging. A drop of water weighing 0.48 grams condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees Celsius. If the heat released during condensation goes only toward heating the metal, what's the final temperature in Celsius of the metal block? The specific heat capacity of aluminum is 0.903 joules per gram degree Celsius. So I would expect that this would be somewhat confusing. So let's draw a picture. So here's my block of aluminum. I'll call him Al. And Al weighs 0.48 grams. No, Al doesn't weigh 0.48 grams. That's the water. Al is 55 grams. He's a big guy. And it also tells us that the block of aluminum is initially at 25 degrees Celsius. So it's at 25 degrees Celsius. And then it is a drop of water. So water's blue, right? So here's a drop of water. Kind of looks like a Hershey's Kiss, makes me want chocolate. The water has a mass of 0.48 grams. So we've got water in the gas state condensing into a liquid on this block of metal. And it's telling us if the heat released during condensation goes only toward heating the metal. Could we figure out how much heat is released when 0.48 grams of water condenses? Yeah. Sure we could. We just learned that the heat of vaporization is 40.7 kilojoules per mole. Right? It's on this table too, back here. $40.7. Oh, but look, this is at the boiling point. Do you think this is happening in a boiling situation? Probably not. Probably it's more at room temperature. So then the heat of vaporization is 44 kilojoules per mole. So let's use that one. So we want to calculate how much heat is released when 0.488 grams of water condense. So we've also got 44.0 kilojoules per mole. That is the heat of vaporization for water. So to calculate the amount of energy that's released, we're going to have to go from grams to what? Kilojoules. We need to go to kilojoules, but can we go directly to kilojoules? We need to go to moles first. So we want to get to moles of water, and then we can get kilojoules. So we'll have moles down here and grams down there. So we know that it's 44.0 kilojoules per mole. We need to know how many moles. 0.48 grams, we're going to use the molar mass of water. So 0.48 divided by 18.016 times 44. So that would have two significant figures, 1.172 kilojoules. That's energy that's released by the water when it condenses. The problem is suggesting that this amount of energy goes into the block of aluminum to heat it up. Do you remember doing calculations like that? Q equals M cap. Q equals MC delta T. So when we have things heating up, we've got Q equals MC delta T. And a clue that you might need that is the specific heat capacity of aluminum. And you know, even if you forgot the equation, you could just look at the units on here and combine this number and that number and this number and get the units to work out and still get the right answer. That's what I love about units. So Q is heat, right? The heat was released by the water, it's absorbed by the aluminum. So this is our Q right here. And we need the mass. Well, we got the mass of aluminum. And we've got the specific heat capacity up here, that's the C. And what are they asking us to find? Temperature, the final temperature. Well, this equation is going to allow us to find the change in temperature. So let's find that first. Rearranging the equation, we're going to get delta T equals Q divided by MC. So the Q is 1.172 kilojoules, M is 55 grams, and C is 0.903 joules per gram degrees Celsius. Let's check out the units. The grams cancel. Does kilojoule cancel joules? No. We need to do something. We can't have this kilo in here. What if instead of writing kilo, we wrote what it meant? I mean, you can convert it separately. But what if we've said, well, that many kilojoules, instead of writing the prefix kilo, I'm going to write what it means. Kilo means 10 to the third joules. Now I've got joules that cancel joules, and I'm left with temperature, degrees. So 1.172 EE3 divided by 55 divided by 0.903 says our temperature change is 23.598. Only 2 sig figs actually because of the 55 degrees Celsius. Is that the answer to the problem? Is that the final temperature? No, because that's lower than this. It started at 25 and it heated up. This is the change in temperature. So if it started at 25 and it's warming up, then I want to add this to the starting temperature. So I'm going to add 25 to that and end up with 48.598 degrees Celsius, which would round to 49 degrees Celsius.
Are we expected to know how to do this?
This is a complicated problem. I wouldn't give you one of these on an exam.
Sounds good.
But it's good to think about and stretch your mind. Any questions? Yeah.
So wait, we have like how many more tests left before the final test?
2.
2. So we should like, sorry, should we review the old stuff like MC delta T?
I would continually be checking back on the old stuff. The nice thing about a 6-week session is there's not as much time to forget things.
Yeah, there
So-
it is.
Well, I'm not saying there isn't enough time to forget things, because there certainly is. I mean, I can forget things that happened 2 minutes ago. Someone can introduce themselves and tell me their name, and we have like 5-minute conversation, and I can't remember for the life of me what their name is, right? So you have to go over and over these things. But there's not as much time. During the regular semester, you have 18 weeks to forget stuff. And then it's really easy to forget. So this is a more reasonable question that could be on an exam. Calculate the amount of heat in kilojoules required to vaporize 2.58 grams. I did that one. Never mind.
Yeah.
But that one was more reasonable. This one's not reasonable. Okay, end of section.